Hi guys, this is part one of, a four-part series about how magnetic fields affect moving charged particles. I realize we haven't talked about what creates a magnetic field, and we're not going to in this video. We're simply going to start by postulating there exists something called a magnetic field, and let's see how it affects a moving charged particle. So here are a couple of equations for you. When we talked about electric fields and the forces on charged particles in electric fields, we said that the electrostatic force was equal to the product of the charge of the particle in the field and the electric field. Similarly, if we're talking about the force on a charged particle in a magnetic field, we get the expression that the force resulting from the magnetic field is the charge of the particle times the velocity of the particle cross product the magnetic field, which is represented by B. A couple things to note: this force, of course, is a vector because you're multiplying a scalar, the charge, by a vector, the electric field. This force, it looks like a vector, but it's kind of a pseudo-vector, right? Remember, a cross product gives you what's called a pseudo-vector. You can also combine these two equations to get what's called the Lorentz equation, which just says the force on a charged particle is the magnitude of the charge Q times the electric field plus the velocity cross product the magnetic field. And this is kind of implicit in the first of Maxwell's laws. Okay, so that's the equation. Most of what we're going to talk about today is we're just going to pretend the electric field is zero, but of course it is an interesting expression if you figure out what happens if a charged particle enters crossed electric and magnetic fields, something like the Hall effect. But let's just assume our electric field starts at zero, and let's see the behavior on a charged particle in a uniform magnetic field. So in this example, we have a uniform magnetic field that's pointing into the page. That's represented by the green X's. And of course, the X's come from an arrow notation you may remember. So if you think about an arrow, if you imagine an arrow coming into the page or going into the page away from you, what you see is the back of the arrow, so you see X's. If you see an arrow coming out of the page at you, you see a dot. So this is the in-out notation that we use to make three-dimensional drawings on two-dimensional paper. So that's a uniform magnetic field going into the page. Now let's add a charged particle. So I'm going to have this charged particle right here, positive Q, or just positive, and it's going to have a velocity to the right. So this particle is going to enter the magnetic field. It's getting closer and closer. Oh my God, what's going to happen? Well, of course, as soon as it enters this, it's going to feel a force in it. What's the direction of the force on this charged particle when it's in the magnetic field? We need to use the right-hand rule to determine that. So grab your favorite color and draw a right hand. If I want to find the magnitude of the force, of course, I'm just going to take my Lorentz equation, and I'm going to say that the magnitude of the force is the magnitude of the charge times the magnitude of the velocity times the magnitude of the magnetic field times the sine of the angle between the velocity and the magnetic field. In this case, my velocity is, whoa, that changed size quickly. My velocity is to the right and my magnetic field is into the page, so my angle is going to be 90 degrees. So the sine of 90 degrees is going to be just 1, so I just get QVB. Of course, that's not always the case, but in this case it is. Let's find the direction of the magnetic force. So using my right hand, I'm going to do V cross B. So what that means is I start by pointing my fingers in the direction of the velocity. So my right fingers are pointing to the right. If you just take your right hand and point your fingers to the right, you can rotate your wrist any way you want. An animation would be nice here, but sorry. You can point your fingers to the right and have your thumb pointing up, out at you, or down. That hurts your wrist, or down into the page. What we want to do is we want to rotate our hand so that we can have our fingers pointing to the right and our fingers can curl in the direction of the magnetic field. So when my fingers curl in the direction of the magnetic field, that means my fingers are going to curl inwards. So when I curl my fingers in or down into the page, what happens is that I fix my wrist in that position so that my fingers were pointing in the direction of velocity. My fingers are now curling into the page in the direction of the magnetic field, and as a result, my thumb is pointing upwards. So that means the direction of the force on the particle when it's in this particular magnetic field is going to be upwards. That, of course, means, if you think about it, if my velocity is a little bit to the right and my force is a little bit upwards, then I'm going to have a change in direction, and ultimately I will get a curved path of this particle. And we'll look more in depth at this curved path in the next couple of videos. The one thing I really want you to notice right now is that you've got a right angle between the force and the velocity. So any change in displacement, any delta x is going to be in the direction of the velocity, and any delta v, or for your force, is going to be in the direction upwards. Since these two are always at right angles, what you can notice immediately is that the total work done, which of course is going to be the integral of f dot dx, that by definition is going to be 0. So the magnetic field is not going to do any work on the moving charged particle, so that means there's going to be 0 change in kinetic energy. So of course magnetic fields can make a particle change its direction, but they cannot speed a particle up or slow it down. One last comment is, what if we don't have a nice force at right angles to our magnetic field, or we don't have a nice angle well defined between our velocity and our magnetic field? What if that is not easy to find? Well, then you have to pull out the full determinant expression and say that the magnetic force is the charge times the determinant of I hat, j hat, k hat times the velocity, that's supposed to be a y, and the magnetic field. And then you actually have to go ahead and calculate the determinant of that matrix, and that'll give you the magnitude and also the direction of your cross product. So please do the problems that I have a sheet for with the sub. When you're done, there are a set of solutions on the Google Classroom which I'd like you to check.